Okay guys, let's take a look at our lesson for today. This is on logarithms. Now the one thing is, really what we're going to be looking at today, there's nothing really brand new. We're just looking at logarithms as a whole. We're bringing a lot of the concepts together today. Talking about just different aspects of logarithms. So just as a reminder, these top ones are just a reminder. The domain of natural log of x goes from 0 to infinity. The two limits would be apparent from the graph. So if we're headed to 0 from the right, natural log is going to negative infinity. And if we're headed to infinity, so is natural log. The range includes all numbers. And this is just information about the graphs, continuous increasing 1 to 1, and it's concave down. So just some general information about logarithms. This next part is really applying what we have already learned. So the natural log, if I take the integral from 1 to x of 1 over x, I get of 1 over t, I get natural log x. And this is taking in what we learned with the fundamental theorem part 2, where we do the derivative of the integral. Derivative of the integral is going to give us 1 over x. So just really some specifics using logarithms. Back to pre-cal on algebraic properties. We've already used them quite a bit this year. It's just a reminder. If we have multiplication in the argument, we're allowed to split them apart by addition, division in the argument, split by subtraction, and we're able to rewrite this as ln of c to the negative 1, pull the negative forward. And I think this is a fairly clever way. We need to know that we can, and this is used quite a bit, that if this exponent is in the argument, we can pull it forward. If it's on the function itself, we cannot pull it forward. Those are two completely different patterns. So the exponent would need to be on the argument itself, and if that's true, then we can use a logarithm and pull it in front of the logarithm. And these, again, we would have learned these in pre-cal. This particular value, it's important that you know that, just memorize that you know that natural log of e is 1. It's something that you would be expected to know. I've seen it pop up on the AP test frequently. Here, natural log of e to the x simplifies to x. This, I think, is a fairly clever way to rewrite. If I take the r up into the argument, I have e to the ln of ar, and the e to the ln simplified just with a to the r. And so we've actually seen this, or we will see this quite a bit. The last one is change of base formula. It's pretty handy. It's not really that handy to use a change of base formula. Your calculators, can do that now without having change of base formula. But in solving equations or substituting, it's quite handy to be able to do that. So this is change of base formula. And as a reminder from our old friends from, gosh, I bet September, these little guys right here, just another, we're bringing all natural logs together. Natural logs in derivatives, limits, and integrals, just all in one lesson to review natural logs. That's kind of how important it is so that we get it all together and refresh our memory. So let's take a look. We got some examples on the next page. On this first example, this is just from a lesson that we just recently did on fundamental theorem part 2. If we do the derivative of an integral, we realize that if this is just an x, then the answer is going to be the integrand with x's instead of t's. If it's something other than that, then we're going to have to chain it. Yeah, we're going to have to go ahead and put the sine x in. So we get 1 minus sine squared x, and then we're going to have to chain it because it's not a plain x, it's sine x, and the derivative of sine x is cosine x. So 1 minus sine squared, we would have to simplify, and I'm sure we know our Pythag by now, right? 1 minus sine squared is cosine squared. So cosine squared x times cosine x would give us cosine cubed. So Just a bit of a reminder from the lesson from a couple of days ago. The next one is our old friend. If there's a pattern, I would recommend that you know the pattern. I'm actually going to do this both ways. We'll talk about what the answer is with the pattern, then we're going to work this the way we would have when we did limits on these back several months ago. So do we remember the pattern? What is the answer to this? It's e to the 1/2. Okay. Really, really need to go know the pattern. Now, I'm going, in case I give you one that you can't work with the pattern, we're actually going to, in a good refresh of memory, we're going to go through the process of how do we do this limit if there isn't a pattern possible. So, what we would do, we think about infinity being here, and that tends to 0. So I would have 1 to infinity. And that's one of the indeterminate forms. Remember, there are 3 types of indeterminate forms that we, depending on which type, told us what to do. So do we remember what to do when we got the 1 to infinity? We almost. This is one where we have to do the y equals and do natural log of both sides. We introduce a dependent variable. So this is one where we intro y equals, and then we ln both sides. That's this type, 1 to infinity. So let's do that. So we're going to say y equals limit x goes to infinity of 1 plus 1 over 2x to the x. So I introduced a dependent variable. Now I'm going to take the natural log of both sides. So natural log of y equals limit x goes to infinity. I'm going to go ahead and do 2 steps at once. I'm going to do the natural log of this, but I'm going to pull the x in front of it at the same time. So x natural log of 1 plus 1 over 2x. Alright, so now let's try again. Let's sub in again. If I sub in infinity, I get infinity, and this tends to 0, and ln 1 is what? 0, so I get infinity times 0. Now this is the second type of indeterminate form. Isn't this awesome? We get to see all types in this one problem. So which type is this when we have, this is the rewrite. This type is the rewrite. Okay, so let's rewrite it. We need to get it in fraction form so that we can force it to be, hopefully, a L'Hopital, so we can do derivative top and bottom. So I'm going to take this x, and I'm going to flip them upside down, turn it into a complex fraction. So limit x goes to infinity, natural log of 1 plus 1 over 2x over 1 over x. Okay, let's try this again. If I sub in infinity, I get, this tends to 0. Natural log of 1 is 0, and this will tend to 0. So finally, we are in the type of indeterminate form where we can use L'Hopital. So we're going to use L'Hopital. So left side, we're just leaving alone. So limit x goes to infinity. So the derivative of a, now remember L'Hopital, right? It's not quotient rule. We take the derivative of the numerator and the derivative of the denominator separately. All right, it's not a quotient rule. It's a technique. So the derivative of natural log is 1 over the argument times the derivative of the argument, right? And the derivative of 1 is 0. The derivative of 1 over 2x is negative 1 over 2x squared, right? With me? So I'll write it out here because I'm seeing some blank looks. So 1/2 x to the negative 1, right? I bring the negative 1 down, and then I subtract 1. So it would be negative 1/2 x to the negative 2, which is this, right? We okay? All right. And that's over, and then the derivative of 1 over x is, negative 1 over x squared, or negative x to the negative 2. All right, so those 1 over x squareds go away. I have the 1/2 left. Those negatives cancel also. So I got the 1/2 left. So let's just kind of work this through in our head. So let's take the limit. So I have a 1/2 left here. And what's going to happen to this piece? It's going to tend to 0, right? Because as the bottom gets bigger and bigger, it tends to 0. So I have 1 times 1/2. So I have natural log y equals 1/2. And then we solve for y. So e to the 1/2 equals y. And our answer is 1/2, e to the 1/2, which is exactly what it was when we did the pattern, if you remember. So I suggest, really suggest that you do memorize the pattern. On the AP test, the vast majority will be using a pattern. They won't be ones that you have to work out like that. Now that doesn't mean that I'm not going to have you work one out like that. That just means that you definitely need to know the pattern. All right. So let's take a look at our last problems. These we're given some information. ln A equals 2 and ln C equals 5, and we're asked to find these integrals. Alright, so let's do that. So the integral of 1 over t is ln absolute value of t evaluated from 1 to AC. Okay? So let's evaluate it. Now, if I can eliminate the absolute value bars, I would want to, because that would be in simplest form. If I can, I should. If I can't, I shouldn't. What do we know about A and C? Do we know whether they're going to be positive or negative? We do, right? They have to be positive. So when I sub this in, I don't need the absolute value bars anymore. It actually, to be proper, to write it properly, it would just be parentheses. ln AC minus ln 1. Okay? We okay? Alright, so what is ln 1? 0. So I'm left with ln AC. I don't really know what that is, but I bet that if I used a log rule, I could figure it out, right? ln A plus ln C. And do we know what those are? We do, right? ln A is 2, ln C is 5, so that integral equals 7. And so that's one way that you'll see problems worked with natural logs in the abstract like that. We okay so far? Yes? Okay. All right, let's take a look at this last one. So we're going to integrate here. We have ln of 1, oops. We get ln absolute value t evaluated from 1 to 1 over c. So again, we know that 1 over c is positive, don't we? Because we know that c is positive. So it's ln 1 over c minus ln 1. And we just all agreed that ln 1 is 0, so that's not a concern. ln 1 over c, I don't really have that, but I can use a rule, right? I can do ln c to the negative 1. We okay with that? That's just algebra. Then I can pull the negative 1 out front. Negative ln c. And so we know ln c is 5, so our answer is negative 5. Yes. Yes, you could. You could split it that way also. Same thing. But yeah, that would be appropriate as well. You can use that log rule where we do ln 1 minus ln c. You bet. How are we? That's a log rule with the division, right? The ln 1 minus ln c. We're going to get the same answer. It's just using a different log rule. We okay?